Hi, this is James Banks. Today I'll be talking about my results for the final of the fall 2021 ADTA 5560 Recurrent Neural Networks class. As you all know, there were 7 parts to this final, and we were asked to ensure that we talked about each one in this video. However, instead of talking about the data in part 1 and then interrupting the flow to go back and cover the unrelated topics of simple RNN modeling of sine wave data, I'm going to cover parts 2 and 3 first so that the data is discussed near its relevant sections, which are the modeling techniques used to forecast that data and the results. But rest assured, I'll cover all 7 parts in this video. So part 2 dealt with creating a simple recurrent neural network as we had done in the midterm and homework sections earlier in the semester. In my case, I generated a sine wave using 2048 observations and evenly spaced the numbers between 0 and 128. I used the 80-20 rule to split out 20% of the data to hold back for testing. As directed, a layer 2 network was created. I used 64 neurons in the first simple RNN layer and then a fully connected dense layer as the output layer. You can see the network design on the right. Remember, we don't count the input as a layer, so there were only 2 in this design. Using the approaches covered in class videos, I built a sequential model using Keras TensorFlow and added layers with the model add function. As we learned in class, it is fairly straightforward. After building and compiling the model, I needed to train it. Of course, I have to normalize it first, and I had to ensure that the data was in a time series format using the time series generator function. I elected to use a length of 64 past data points to predict the next future data point. I kept the batch size at 1 and elected a small number of epochs, 5. After training with the fit generator function, I processed the test data, that 20% that we talked about earlier, using the predict function. One of the key points at this juncture was to make sure that the test data also included the prior data necessary to generate a prediction for the first point. So we had to combine the last 64 observations from the training set to the beginning of the test data set. After transforming the predictions back to the original scale, we could see the results. I used some Python metrics libraries to report the mean squared error for this model, which was 0.487, and an R squared of 3%. So this meant that only 3% of the variability in my data was being explained by this model. We can see this on the next slide. The top left quadrant is from the final exercise with the parameters we just talked about. I think we can understand why only 3% of the variability is explained. Part of the issue I had with the simple RNN models were the inconsistencies between runs of the data, even with the same parameters. The other 3 quadrants are from the midterm using similar generation and modeling parameters, yet they differ wildly between runs, ranging from a fairly accurate prediction, the bottom left, to what looked like totally unusable models similar to what I saw with the final. I'll bring this up again in the conclusions, but there is some doubt and concern in my mind regarding the validity of these techniques. I'm not sure if it's an implementation problem or a lack of understanding on my part, or if it's just the nature of these neural network models. They are based on initial guesses of random weights and bias assignments. So there is some random unpredictability in their creation, or perhaps this just emphasizes the importance of validation and testing in model creation. But again, I'll talk about this later. The generation of the model's build and train process are relatively similar regardless of type. So I'm going to cover those quickly here so I don't have to repeat them in each section. After obtaining our data, we need to ensure that it is pre-processed and standardized. We need to identify our test data, whether that be using the 80-20 rule or some other ratio. If we're going to perform any kind of forecasting, we need to ensure that we isolate any forecast holdout set as needed. And then for time series modeling, we need to ensure it is in a time series format. With Keras, we use the time series generator function, which requires the specification of a length representing the number of input observations used to make a prediction in a batch size. We then build the model. In our case, it was a sequential model, and we add layers as needed using the model add function, specifying relevant information such as the number of neurons or the drop rate, depending on the type of layer we're constructing. It is also here that we need to ensure that we have a final, fully connected dense layer for output. We then compile our model, which is where we specify our optimization options and our loss metrics. The fit generator function of Keras is used to train the model. This is where we specify the number of epochs we want to run. I kind of view these as similar to the cross-validation parameters we specified in other types of models. We then predict and evaluate the results like we would any other type of model. If we're going to forecast, then we need to retrain the design model using all the data to enhance the predictive capacity. This will include converting the data to a time series using the time series generator function, just like we did earlier. And finally, we would predict and then evaluate the results, just like we did before, once the forecast time period had elapsed. And that's basically the process steps for a time series model implementation in Keras TensorFlow. And now I'd like to show a couple of examples of some of these implementation procedures. The first one is normalizing the data. Again, it's just a very simple a function, the min-max scalar. We've talked about it before. The key item here is to make sure that when you transform your data, make sure that you also inverse transform it back so that you can get the appropriate results. The next item we talked about was the time series generator, and I wanted to show an example of that because that's unique to the time series that we've been studying. Again, some key factors are here: the length, which is the number of predictor observations you're going to use for the next observation, the batch size, and again, the function we use is the time series generator function that we talked about earlier. This is an example of a sequential build for an LSTM neural network. Again, the key here are to define the model as a sequential and then use the model add functions that we talked about earlier to specify the key parameters like the number of neurons, the activation function that you're going to utilize, and use a model add for every layer that you're going to add. And then, of course, again, like we talked about earlier, you want to make sure and end with the fully connected dense layer. The compile and train is interesting, and I wanted to share examples of that. The point, again, it's just the compile function, but the point I wanted to make here is that when we talked about adjusting the learning rate, which I'll talk about again shortly, this is where you can specify that parameter override to get a more appropriate learning rate for your particular situation. Again, as we talk about this, that'll be significant in my situation because of the large number of zero values that I had in my data. And then to train the data, we used the fit generator function. And again, on that, the key parameter is the epochs that you're going to specify. And then, of course, we do the predict and evaluate. For the prediction, we use the predict generator function. And then for evaluation, we've learned about a number of metrics in the past. I, again, use the mean square error and the R squared. And there are functions within Python that allow you to create those or to calculate those metrics quite easily. Part 3 was covering the long short-term memory neural network core concepts of the cell state and the gate. If you recall, the cell state is a mechanism to provide information from the beginning to the end of a sequence, which is what makes the memory portion of the model. In the top right, we can see the cell state channel or track. In class videos, the cell state was described as an interstate highway. but I like to think of the channel as a train track instead of a highway. Just as a train carries cargo freight between depots and cities, the cell state carries information along its track or channel. And just like the cell state adds and removes data from the cell state as needed, the freight train adds and removes various freight cars from its sequence. The rail cars are loaded and unloaded with cargo or information as they pass through from depot to depot, having cars added or subtracted until the cargo eventually ends up at a final destination, or in our case, the output layer. In my mind, this best describes what the cell state does as the data is passed from cell to cell and modified, data added and removed until it is eventually output. Just like the train following its track from the first to the last depot on its route, the cell state travels from the beginning to the end of the sequence. The train analogy really works for me in understanding the process. This information from earlier parts of the sequence chain provide an implementation for short-term memory by providing the ability to recall what occurred before in the sequence. In addition to this information flow within a channel from beginning to end of the sequence, a snapshot of the cell state is also available. You can see this in the C sub t in the topmost figure. In addition to the cell state, the LSTM neural network utilizes three gates. They are the forget, the input, and the output gates. The gates regulate information flow along the path of neurons or network cells. In addition to the LSTM cell using an activation function, like all the other neural networks we have seen from the Macaulay-Pitts model to the simple RNN, each of the three gates also uses an activation function, the sigmoid function, to control what information is passed forward or removed. In comparing the similarities and differences between the LSTM cell state and the hidden state of the simple RNN, there are several interesting observations. From my perspective, the most interesting similarity is that the cell state is in essence a hidden state in its own right. If you remember the simple RNN, on the right, you can see that the hidden state is based on an input, and the activation function, and the prior hidden state. If you compare the figures, you can see that the cell state, C sub t, is adjusted based on the input, the prior hidden state, and the guidance of an activation function. Almost just like the simple RNN hidden state, H sub t. It is basically just layers within layers of hidden states. With regard to differences, the simple RNN hidden state is passed forward, so there is no reference backwards through the sequence. Each hidden H sub t is modified without reference to the earlier sequence. However, the cell state, C sub t, provides a reference back to the earlier sequence entries. That's the memory. I see that as the primary difference between the hidden state of the simple RNN and the cell state of the long short-term memory cell. Now I'm going to jump back and pick up part one because I think it's going to flow more naturally into the next set of conversations. The first thing I want to state is that I'm not a geologist. I was raised in Oklahoma and I have a lot of family still living in the state, so I'm constantly hearing how earthquakes have increased. Each of my family has their own theory as to why, and typically fracking is blamed. For those of you that don't know, fracking is a method for extracting oil from shale. While this is not a research paper focused on geology, environmental, or oil and gas industry processes, I was curious if I could see any connection or patterns regarding increased earthquake activity and if there was a model using time series methods that I could equate it to. With some quick research, I found the USGS, US Geological Survey, which is a government organization, which reported that there's been a surge of earthquakes since 2009 in Oklahoma. They believe that the culprit is primarily wastewater disposal. And in fact, after pulling some data about Oklahoma earthquakes from 1960 through September 29, 2021, you can see this spike. This data was downloaded from the University of Oklahoma Geological Survey Earthquake Catalog Download Tool. That's kind of a mouthful. And I have a reference to it in the back. Note that I only pulled data for earthquakes with the magnitude of 2 or more. I started out with over 27,000 records or earthquake events, but it wasn't really a time series data because I could have more than one event in a given day. So I aggregated the data using the pandas group by function by date. I then also added a new record for any missing data with a frequency of 0 indicating no earthquake occurred that day. I ended up with 22,177 records representing each day between January 11th, 1960 and September 29th, 2021. I've included a listing of all the original data fields in the download. Note there were inconsistency in usage of the fields over the years. Some fields were discontinued after 2018 and some new ones were utilized after 2018. I primarily used the origin time, that's the date and time the event was believed to have occurred, the magnitude or the severity of the quake, and the frequency, that's how many quakes occurred that day. Logically, I felt that I should use both magnitude and frequency in the model, but as we were instructed to only use one numeric variable as a predictor, I settled on frequency as my primary numeric variable. I did use latitude and longitude and county for some graphic representations, as you'll see shortly, but frequency was my key variable. When I began attempting to utilize the 22,000 records, I almost immediately ran into issues with memory problems on my Google Cloud Platform virtual machine. I tried upgrading my virtual machine from TensorFlow 1.15 to 2.6, which did help and allowed me to proceed forward. However, the processing time was very slow, so I elected to reduce the size of my data from 22,000 to 3,653 records representing the 10 years between September 29th, 2010 to September 28th, 2020. You can see it represented in the lower left plot. Of course, I kept the forecast data we talked about earlier, representing the last year of the activity. I performed some simple exploratory data analysis, including a histogram that you can see on the right. It was interesting to note that there was an average of almost 7 earthquakes per day in Oklahoma during the 10-year period, with the highest being 73 on a single day. Just comparing that to the original sequence of data from 1960, you could easily see that there was something going on within the state. I would have liked to have used Python, but it looked a little complicated, so I used Tableau, which we learned about in the prior ADTA class, to visualize the location of the quakes in the state. Remember, I was only looking at earthquakes that measure 2 or greater in magnitude. And just for your reference, this is where my family primarily resides in northern Grady County, so there was definitely earthquakes occurring in the area. For my first model, that's part 4, I kept it pretty similar to what we did in prior exercises. I created a 6-layer model as seen on the right. It has 3 LSTM layers with 64 neurons each and 2 drop layers using a 20% dropout rate. And of course, the final fully connected dense output layer. Similar to what I described in the sine wave model, we went through a build and train, including normalizing the data and creating a time series using the time series generator function of Keras TensorFlow. I used a batch size of 64 and 365 historical data points to predict the future point. For some reason, I thought that since I was predicting some long-term ecological event that I needed to look back longer historically before predicting. It made sense at the time, but as you'll see when we compare results, it started me down a path that may not have been the best one. The bottom line is that it caused me a number of issues, the first of which, it made it difficult to run larger epochs, and I had a number of timeout issues with GCP connectivity. And note, my computer was not set to go to sleep or hibernate, so this wasn't the issue. As a result, I had lowered my epoch count just to get through my model. My second issue was that my results kept returning NaN, indicating that the model had stopped learning and generated no predictions. I resolved this issue by researching and changing my learning rate from the default of 0.001 to 0.00001, which allowed me to obtain predictions and forecast. And this was a simple option specified at model compile time. Regardless, my results on the test data set were poor, with a mean squared error of 7.78 and an R squared of a negative 1.07. I had to research to see if a negative R squared was even possible. It was, but clearly my model was not good. I've shared the prediction compared to actual frequency on the left, the model loss plot on the top right, and my forecast on the bottom right. It was funny and a little disheartening to see that my average actual frequency in the forecast was 2.158, and my lengthy model generation had pretty much just returned the average. I could have probably done that with a calculator. So then I set about trying to redesign the neural network. I tried a number of different options, but I also didn't want to change too much too drastically, as I wanted to try to better understand the parameter impact to the model. And we'll see the results of some of this in part 5. In the redesign that had the best results, I had retained 3 LSTM layers with 64 neurons. But because I was seeing almost no fluctuation in my prediction, if you remember, it was almost a straight line, I reduced the drop rate. My understanding was that the drop rate was to minimize overfitting. Well, since that certainly wasn't occurring, I felt safe in reducing these pretty dramatically. I chose a drop rate in the 2 layers at 0.5%. I reduced my historical data points as input from 365 days to 30, thinking that perhaps my idea of the importance of a lengthy input sequence to predict a quake was false, and that since they were occurring almost daily, a smaller input sequence might give me more current input. The batch size remained the same, but since I had a smaller input length, I was able to achieve 100 epochs relatively quickly. I retained the lower learning rate to keep the model learning. As an aside, based on subsequent research, I think this problem was caused by the large number of zero entries representing no earthquakes occurring in the sequence. The bottom line was my evaluation with test was much better, achieving a mean square error of 3.5 and a positive R squared of 5%. Of course, that's really still pretty poor, indicating that only 5% of the variability of the data was being explained by the new model. I was excited to see the positive R squared and at least some movement in my predictions, as you can see in the comparison of actuals to prediction on the left. The loss plot was more dramatic on the top right. However, the forecast on the lower right was just not reflective of what actually occurred for the next year of data. The model was clearly not a good predictor of earthquakes. As I said earlier, I made a number of various models, and we can compare some of those for part 6. Again, I tried not to change too much too rapidly so I could hopefully gain some understanding of the impact of the parameters. All the models were LSTM with a batch size of 64. The learning rate was consistent for all at 0.00001. I used the ADAM optimization mechanism and a loss metric of mean square error. I did vary the length, the number of epochs, the layers, and activation functions, as you can see in the table. As I noted earlier, I had mistakenly reduced my epochs due to performance issues with GCP, and I think that cost me with regard to predictive accuracy in part 4. I could consistently see better results when using a higher number of epochs. The 365 length with 100 epochs had comparable performance to the best model, so it wasn't the length of the sequence that had hindered my earlier prediction, it was the smaller number of epochs. I even did a model with no dropout layers and a 60 neuron layer, 30 neuron layer followed by a 15 neuron layer with a final dense output layer, which achieved similar results after rounding to the best model. But still, the best model was the 30-day input with a 0.5% dropout rate, which achieved a mean square error of 3.5 and an R square of 5%. Of course, as we talked about earlier, that still just wasn't a very good model. There were a couple of lessons learned that I'd like to discuss. The first one was that learning rate adjustments seemed essential if the model stopped learning. Remember, in my case, because I had all of the zero entries, remember those were the ones representing no earthquakes on that day. So because I had so many of those, I ended up with a NAN or missing results during the training for the loss and during the predictions and or during any of my forecast attempts. I had verified that I had no missing data in my data set, but again, after research, I determined that the zero values were the most likely culprit and were impacting my model. And the recommendation was to decrease the learning rate parameter. This worked, and I was able to generate a model, but it emphasized the importance of this parameter. Epics play a much more significant role than I had assumed in improving results. Remember, I had virtual machine memory issues with TensorFlow 1.15 on a 32 gigabyte machine with 8 virtual CPUs on the Google Cloud platform. So there seemed to be some type of memory leak, or perhaps my length was just too large. Regardless, I decreased my epoch size, which allowed me to generate a model. However, the results were pretty poor. Regardless, this misinterpretation of the importance of epochs cost me with regard to the validity of my earlier models. I should have stayed with the larger epochs. As I mentioned, it's easiest for me to relate to these as the cross-validation parameters we specified on other models. Not sure if this is a correct analogy, but it keeps it straight in my mind. Of course, parameter tuning was important in obtaining a good model. When I changed epochs or links, and especially learning rate, I could see varied results with some improvements. Had I had more time, it would have been interesting to explore these various parameters, but as we've seen with other non-neural net models in the past, the parameters are definitely important. As I mentioned earlier, the model results were often inconsistent and difficult to recreate, even using the same parameters and data. I saw this with both the simple RNN and the long short-term memory models. I talked about it earlier in the presentation. This was troubling, but again, considering these models are based on initial random weights and bias measurements, I suppose it isn't that surprising. However, it does lead to the next point, which is that it is essential we perform validation and testing of the models. Without this critical step, there is no way to know if the model is even close to accurate. And as we saw in our examples, the neural networks could easily and arbitrarily take off on tangents which in no way reflected the reality of a situation. I would also argue that this needs to be an ongoing exercise. I could easily see the results and model predictive accuracy changing with time. And in conclusion, it appears that earthquakes are not time-based. This probably shouldn't be surprising, as we have eons of geologic effects at play, which are probably not particularly relevant to what happened yesterday, last month, last year, or even the last several decades. It would have been really interesting to see the impact of other variables such as location or magnitude to see if they could have enhanced the predictions, or even more interesting to see if like drilling or wastewater disposal information could have been incorporated into the model to see if those might correlate within the neural network to determine if those facts might have enhanced the predictions also. However, at this point, I have to conclude that I was not able to produce a viable model for Oklahoma earthquake predictions. Here are my references if you'd like to research further or see the data for yourself. And thank you very much for your time and good luck in your future classes. If you have any questions or suggestions, please feel free to reach out to me at jamesbanks@myunt.edu. And that concludes this presentation.